Hello friends, in this video we see the topic congruent modulo n. Let n be a fixed positive integer. Two integers a and b are said to be congruent modulo n, symbolized by a congruent to b modulo n. If n divides a minus b, that means n divides the difference a minus b. Means if n divides a minus b, we have to say that a and b are congruent modulo n. That means a minus b must be equal to q into n for some integer q. Means if you have an integer q for which a minus b is equal to qn, then means that n divides a minus b, and n divides a minus b means a is congruent to b modulo n. Let's see some of the example of congruence modulo n. So note that 27 is congruent to 12 modulo 5 because the 27 minus 12 is nothing but 15 and 5 divides 15 means 5 divides 27 minus 12, so 27 is congruent to 12 modulo 5 by the definition of congruence. Let's see another example. 10 is congruent to minus 6 modulo 4 because 10 minus minus 6 is nothing but 10 plus 6, which is 16, and 4 divides 16 means 4 divides 10 minus minus 6, so 10 is congruent to minus 6 modulo 4. Let's see another example. Minus 4 is congruent to 5 modulo 3. Since minus 4 minus 5 is equal to minus 9 and 3 divides minus 9 means 3 divides minus 4 minus 5. So this minus 4 is congruent to 5 modulo 3. Let's see another example. Minus 10 is congruent to minus 4 modulo 2 because minus 10 minus minus 4 is equal to minus 10 plus 4, which is minus 6, and 2 divides minus 6. So minus 10 is congruent to minus 4 modulo 2. Let's prove one theorem related to congruence of a and b modulo n and the remainders of a and b when divided by n. Let's see the statement of theorem. For arbitrary integers a and b, a congruent to b modulo n if and only if a and b leave the same non-negative remainder when divided by n. The statement of this theorem says that suppose we have an integers a and b, and a is congruent to b modulo n, equivalent to when we divide a and b by the same positive integer n, then leave the same non-negative remainder. Let's prove this theorem. Suppose a is congruent to b modulo n. So by definition of Congruence n divides a minus b means there exists some integer k for which a minus b is equal to k into n means a is equal to b plus kn for some integer k. Upon division by n, b leaves a certain remainder, say r. That is, b is equal to qn plus r, where r is greater or equal 0 less than n. Therefore, by replacing the value of b qn plus r in a is equal to b plus kn, we get a is equal to b plus kn means in bracket qn plus r plus kn, and by taking n common from qn and kn, we get q plus k in one bracket into n plus r, which indicates that a has the same remainder as b when divided by n. See, after dividing b by n, the remainder was r, and here you can see that after dividing a by n, the remainder is r. Means here we got the same remainder dividing both a and b by n. This is one part of this theorem. Let's prove its converse part. Conversely, suppose we can write a is equal to q1 n plus r and b is equal to q2 n plus r with the same remainder. Note that the remainder is always greater or equal 0 and less than the divisor. In this situation, the divisor is positive integer n, so r is less than n. Now, by taking difference a minus b, we get in bracket q1 n plus r minus in other bracket q2 n plus r. By simplifying it, we get q1 n plus r minus q2 n minus r. Now, this r and minus r get cancelled because of opposite sign, and by taking n common from q and n and q to n, we get q1 minus q2 in bracket into n, means we have a minus b is equal to some integer q1 minus q2 into n, means by definition of divisibility, this n must divide a minus b, and by definition of congruences, a must be congruent to b modulo n is proved, means we have proved the converse part also. I am stopping here. Thanks for watching the video. Thank you.